We're going to put our explorer hats on for hopefully only 12-ish minutes and pull sort of a Magellan, but instead of going around the world, we're going to go into the world. So my project this summer was doing a first round of analyses on the continental crust, which is Earth's outermost surface in an area of central Colorado. And the basis for this analysis is a method that my research mentors have been working on, combining seismology and structural geology to understand the geometry of the subsurface. And if you're not really familiar with the concept of geometry related to the Earth, it's somewhat similar to what's going on in this building structure in that you have beams dipping in all different directions, and we have a similar variation in orientation of rocks that we can see at the surface, like in the flat irons, but we want to know what it looks like below the surface as well. So the golden question is, why does anybody care about this? And the continental crust has some of the oldest rocks on Earth, and we're talking on a magnitude of billions of years. So they preserve a lot of information that give us a better understanding of how the Earth has evolved over time. This technique also has us using pre-existing data. So we're taking data that has already been established and we're reusing it to understand new things about the Earth that we didn't realize this data could tell us before. And we're applying it with data from another discipline that also was already in existence. And then there's also human implications, because as technology has been advancing, we see human activity interacting with the subsurface more and more. So back home in Nevada, they want to put nuclear waste in Yucca Mountain because they are saying that it's an area of low seismicity. So of course it's going to be safe to store nuclear waste there for the next several thousand years. And also with advancing technology, we have an increased demand for things like minerals. And the ore bodies where we find these minerals are often associated with structures that can go deep into the surface. So my project goals were to take seismic properties determined from hand sample sized rocks and apply it to an entire map area to create an average set of seismic properties for the entire area. We also want to know what orientations of the rocks in the subsurface are the most dominant and how they influence seismic waves as they move to the surface. And then eventually we would like to see how those orientations change at different depths into the subsurface. So seismic anisotropy is one of the fundamental concepts of this method, and it essentially is saying that a seismic wave can move through the same rock at different speeds in different directions. So on the left, we have a picture of a gneiss, which is a common metamorphic rock here in the Rocky Mountains. And you can see alternating bands of light and dark minerals. And on the right, we have an image explaining how seismic anisotropy works on a basic level. So you have the red wave moving along one band, and then you have the blue wave moving through several bands. And so that anisotropy tells us that the red wave is going to move faster than the blue wave, and the difference in time between the two can give us insight into the rocks that they've traveled through. And then we're linking this to surficial geology by taking measured orientations of rocks from published geologic maps and incorporating these actual measurements with seismic properties, which is a shift from previous models that have made a lot of assumptions about how the rocks are oriented. So to do this, one thing that we've had to resolve is the scale difference between the seismic properties that we have and what we want to apply them to. So we determine properties at the thin section scale, which is millimeter maybe, and we want to apply it across an entire map area, which can reach tens of kilometers. So this is my study area. It's the Denver West Quadrangle. And on the left, we have the original geologic map, which, as you can see, is really complicated. There's several different units. And on the right, we have a simplified geologic map where we reduced it down to these 4 units, which are considered to be dominant in the composition of the crust. And they have very specific ways that they influence seismic waves that move through them. So as I said, we already have seismic properties from hand sample size rocks. So pretty much how those are determined are we get a rock, we take a very thin slice of it, put it under a microscope, and we get something like the image on the top right. And essentially, you can create a map of the thin section and determine what crystals there are and how they're oriented, and then take the average of the whole thin section to create an average of seismic properties for the thin section that can be then applied to the rock that it came from. So I wanted to apply this process to an entire map, and how I went about doing that was I created a pixelated version of the simplified map that we developed with the 4 different lithologies. And the image on the right is an example of what the map might look like zoomed into a certain area. And each cell, is treated like a thin section, but instead of treating each cell as a specific mineral, we're applying a specific type of rock. So the purple is a granite, and then we're also saying that that specific cell is oriented a certain way. And then we come up with an average set of seismic properties for the whole map area. And that allows us to begin to resolve the difference in scale from the millimeter to the kilometer scale, with the eventual goal of being able to apply this at the continental scale, which could span hundreds of kilometers. So once we get our seismic properties, we plot them on these circles at the top called stereo nets. And they're complicated because they are a 2D representation of a 3D object. So you're going to have to use your imagination just a little bit. But on the left, we have an example of a stereo net plot for a sample that has horizontal orientation. So this is pretty much telling us that if a wave travels parallel to one of the layers, it's going to be fast. But then if it tries to go through the top of the rock, which is represented by the red in the middle of this bullseye type pattern, it's going to have to hit every single layer. So when it goes through the red part, it's going to go the slowest. And then on the right, we have an example of what that rock would look like if it were oriented vertically. And so this is telling us that the fast plane of the rock is vertical parallel along the different strata, and the slow axis is horizontal to that. So if you tried to move left to right through that rock, it's going to move a lot slower. So one of the first steps of this process, I took the map that I made, and then I applied a sample to each different unit from a compilation that was made from previously studied rock samples from around the world. And with those, I just assumed a horizontal orientation. And the result, as you can see, is similar to the stereo net from the last image in that it has that bullseye pattern. So that's consistent with what we would expect for that orientation. And the anisotropy in that analysis was about 7.5%, which is in the middle of what we were expecting of between 1 to 2%, or I'm sorry, 1 to 15%. So then I took that same set of seismic properties and I then applied all the orientations to the different cells. And we have this image. So this is essentially telling us that we now, instead of having a fast plane, we have a slow plane, which is that band of red. And it's oriented, it starts up in the northeast and then goes down into the southwest. And then the other side of the blue bullseye is dipping away from us towards west, northwest, so we can't see it. It's also dipping somewhat about 45 degrees. As you can see, the bullseye is sort of in the middle of the stereo net plot there. So then we zoomed into one of the seismic stations in our area out of 2, and we have these results from a 25 square kilometer area and a 100 square kilometer area. And we found that they looked pretty similar, but compared to the overall set of seismic properties, the orientation is more north to south. And you can see the other side of the blue bullseye is now dipping to the west, and it's a lot more steep than the last time because it's probably at about at least a 60-degree angle. So what does this all mean? We compared our modeled anisotropy and seismic properties to what's actually been recorded at seismic stations, and it was not conclusive. So more investigation needs to be done there. However, the average orientation of all the data points that we had from the geologic map was approximately striking southwest to northeast, and it had a dip of 56 degrees, which is similar to that image on the bottom. And we also found that the orientation of the geometry is dominated by the biotite gneiss, which is the top image. It looks a lot like the bottom image, which is all the lithologies. So we determined that the biotite gneiss controls how the geometry is oriented, and the other lithologies just dilute the anisotropy so that the difference in wave speeds isn't as much. So in summary, we wanted to go from the micro scale to the macro scale. And we were able to do that using ArcGIS and the Elastic and Seismic Properties toolbox. And the next step will be doing more investigating, comparing it to actual seismic data. And these are my acknowledgements, and now I will open it to questions.